Now associated with the distribution function of a discrete random variable, I have another function which we call as a probability mass function. And let me introduce that. Let x be a discrete random variable with distribution function fx and support sx. So that sx is same as dx, support is same as the set of discontinuity points, probability x equal to x is positive for every x belonging to sx, and summation x belonging to sx, probability x equal to x is 1. Now I define a function fx which is from R to R, and how do I define fxx is same as probability x equal to x if x belongs to sx and 0 otherwise. So distribution function gives me a probability that x less than or equal to small x. It gives me a probability of every singleton in the set of discontinuity points of x. Now such a function is called the probability mass function. Let fx be the probability mass function of a discrete random variable, x having support sx, then clearly fxx is non-negative. fxx, which is same as probability x equal to x, is positive for every x belonging to sx, because points in sx are discontinuity points, so probability x equal to x will always be greater than 0. And summation x belonging to sx, fxx is 1, because probability x belonging to sx is 1. So a probability mass function satisfies these three properties. It is always non-negative, it is strictly positive for every x belonging to sx, and sum over x belonging to sx, fxx is always 1. Now conversely, if you are given any function g which has these properties, that means it is always non-negative, gx is positive for every x belonging to s for some countable set s, and summation x belonging to s, gx is 1 for some countable set s, then such a function is probability mass function of some random variable y. One can prove this, I am not going to prove it over here. For a discrete random variable with support sx and PMF fx, let us try to see what is its distribution function in terms of probability mass function. fxx is same as probability x less than or equal to x. But you know that probability x belonging to sx is 1, so probability x less than or equal to x would be same as probability x less than or equal to x intersection x belonging to sx. So what I do now is I sum over only those values of x in sx for which only those values t in sx such that t is less than or equal to x. So t less than or equal to x and t belonging to sx, probability x equal to t. This is probability x equal to t, and that becomes fxt. In fact, I could have written probability x equal to t first, and then I could have replaced this by fxt. So note that if you know the probability mass function, you know the distribution function. Let us see what happens conversely. fxs can be written as probability x equal to x. This is positive for every discontinuity point. So this is same as fxx minus if x belongs to sx. Otherwise this is 0. Because outside sx, probability x equal to x is 0. Because it gives whole weight to sx. So any point outside sx will have weight 0. So that means from a distribution function you get a probability mass function. So what do you get? A probability mass function determines a distribution function and conversely. And we have seen that induced probability function can be studied through distribution function. So equivalently, the induced probability function can also be studied through probability mass function fxx. Now one can easily see over here, because distribution function is unique, so the probability mass function of a discrete random variable is always unique. So you cannot have two different probability mass functions for a given random variable x, because probability mass function comes through distribution function from this relation. And since distribution function of a random variable is unique, probability mass function would always be unique. Now let us consider this example. Suppose E is an experiment where you toss a die repeatedly and independently, and you keep tossing it until you get a 6. So x is the number of tosses required to get 6 for the first time. So there is a possibility you get the 6 in the first one, then you stop the experiment. If you don't get the 6 in the first one, then you go to the second one. If you get the 6, you stop at the second, otherwise you further continue. So number of tosses required to get 6 for the first time. So my support would be 1, 2, 3, because x can take value 1, 2, 3 and so on with positive probability. For x belonging to sx, the event x equal to x occurs. What does x equal to x means? That means I have taken small x tosses to get the 6 for the first time. So that means the xth toss I got the 6. And in the first x minus 1 I did not get a 6 at all, because had I got a 6 I would have stopped. So x equal to x occurs if and only if first x minus 1 trials do not result in 6 and xth results in 6. So probability x equal to x is first x minus 1 do not result in 6. So first I don't get 6, so that probability of that is 5 by 6. Second also I don't get 6, probability is 5 by 6. X minus 1 also I don't get 6, that probability is 5 by 6. So 5 by 6 to power x minus 1. Now this product is coming because of this independence. Then the xth one is 1 by 6. So for x belonging to Sx, probability x equal to x is this, and if x is not in Sx, probability x equal to x would be 0. So I got my probability mass function as this. I can get from here distribution function, fxx is probability x less than or equal to x. Now note that if x is less than 1, probability x less than or equal to x would be 0, because probability mass function is giving positive probabilities only for x equal to 1, 2 and so on. Now if x is greater than 1, now note that this x may not be an integer, whereas x gives whole weights to only positive integers. So that means I look at what is the maximum integer contained in this, and I sum probability x equal to 1, probability x equal to 2, probability x equal to maximum integer contained in x. So that is what it becomes. Summation j is equal to 1 to maximum integer contained in x, probability x equal to j, this is same as probability x equal to j, which is same as 5 by 6 to power j minus 1 into 1 by 6 for any x greater than or equal to 1. You can sum this turns out to be 1 minus 5 by 6 to power maximum integer contained in x, if x is greater than or equal to 1. So you could get the probability mass function and distribution function in this example. Let us consider another example. So here you are given a distribution function fx, which is like this. One can easily check that this is a proper distribution function. It is non-decreasing, fx of minus infinity is 0, fx of plus infinity is 1, and it is right continuous because the way these branches have been written. What is the set of discontinuity points? The set of discontinuity points is certainly 2, because at 2 left hand limit is 0, value of the function is 2. At 3 left hand limit is 1 by 6, value of the function is 2 by 3. At 4 left hand limit is 2 by 3 and value of the function is 5 by 6. At 5 left hand limit is 5 by 6, value of the function is 1. So it is discontinuous at 2, 3, 4, 5. So dx is 2, 3, 4, 5. Probability x equal to 2 is same as fx2 minus fx2 minus. One can easily check it is 1 by 6. Probability x equal to 3 is fx3 minus fx3 minus. fx3 is same as 2 by 3 minus fx3 minus is 1 by 6. So this turns out to be 1 by 2. Probability x equal to 4 is same as fx4, which is 5 by 6, minus fx4 minus, which is 2 by 3. So this turns out to be 1 by 6. Probability x equal to 5, which is same as fx5, which is 1, minus fx5 minus, which is 5 by 6. So this turns out to be 1 by 6. So I look at probability x belonging to dx, which is probability x equal to 2, plus probability x equal to 3, plus probability x equal to 4, plus probability x equal to 5. And this turns out to be 1. So thus x is a discrete random variable, and what would be its probability mass function? fxx. It gives only positive weight to its discontinuity points. So it is 1 by 6, 1 by 6, 1 by 6 for the points 2, 4 and 5. So fxx, which is probability x equal to x, is 1 by 6 if x is 2, 4, 5. This is half if x equal to 3, and 0 otherwise. So from distribution function I could get the probability mass function. Now let me give some take-home problems for any discrete random variable so that support is same as the set of discontinuity points. I have given you a proof of this, but still try this of your own. A fair coin is independently tossed 5 times. Let x denote the number of heads observed in 5 tosses. Find the probability mass function of x. We'll later consider a much more general random variable than this, but for the time being try to find the probability mass function of this random variable. Now for any discrete random variable x, so that support is same as this set, collection of all those x belonging to R, such that probability x lies between x minus epsilon to x plus epsilon is greater than 0. So try to do these problems. Now before I conclude, let me give the abstract of the next module, a summary of the things I'll be doing in the next module. Now we have defined discrete random variables through a property of a distribution function fx. Now continuous random variables I'll define in the next module, and they will have a property that your distribution function is continuous everywhere. So for random variables whose distribution function is continuous everywhere, I'll define such random variables to be continuous. Absolutely continuous random variables would be introduced, and these would be random variables whose distribution function can be written as a definite integral. So this was all for this module. Thank you very much for your patience, and have a great day.